Okay, so we'll start from where we left yesterday. So this is what we had seen yesterday. We saw what's the difference between a convolutional neural network and a feed-forward neural network, and we focused on two main properties. One is sparse connectivity, and the other was weight sharing. Yeah, that's about it. And then we saw that this representation of, we saw this diagram about how you could have multiple kernels, and each kernel would apply across the entire image, and the weights would be shared for that kernel. So far, we have only focused on the convolution operation, and even when we have seen the neural network or the convolutional neural network, we have only seen the convolution layers, right? So there is something more in a typical convolutional neural network, and that's what I was about to start yesterday. So we'll just continue from there. So this is what a full convolutional neural network looks like. So ignore these things for now. All these parameters, etc., just ignore for them. I'll just walk you through what is important in this diagram, right? So your input is an image, and the task that you're dealing with here is digit recognition or handwritten digit recognition, right? And what you see here is that you have taken an input which is a two-dimensional input, and the next layer you actually see 1, 2, 3, 4, 5, 6 outputs. So what does that mean? You have used 6 filters, applied them throughout the image. Each filter gave you one feature map, and so in this layer you have 6 such feature maps. So your original two-dimensional input has now become 6 two-dimensional outputs. Okay. After that, there is something known as a pooling layer. We'll see what a pooling layer is in detail. Okay. Now, what I want you to understand is, let's assume that what the pooling layer does is it does some kind of a shrinking. It takes the original output and shrinks it. How it shrinks it, we'll see in a while. But let's see what happens after that. So now you have 1, 2, 3, 4, 5, 6 as your input. So now you have this as your input. This volume is now your input. I call it a volume because it has depth, height, and width. And now you're again going to apply convolutions to that. And what do you see? How many outputs do you have now? You have 16 outputs, right? So what does that mean? I took this 3D input, applied 16 3D filters on it. Each 3D filter gave me one feature map, one 2D feature map. Why one 2D feature map? Because we are doing a 2D convolution. We are taking a 3D filter, but we are doing a 2D convolution, right? And then after that, again, this becomes my input, and then do a max pooling on top of that, and then something else happens after that. So there are, which we'll come to later. So right now I just want to say that there is this input, then you come with some output after applying convolutions. Now this becomes the input for your next stage where you have done pooling. Now the output of pooling becomes the input for the next stage. So you'll take this as the input, apply some convolution on that, get some output, and continue in this way, right? And we'll come back to what these are. Okay. So now let's dive deeper into what is pooling. What does the pooling layer actually do? So here's your input. Again, it's a volume. And now when I say input, you should not just think of the input as this. Remember that all of these can be inputs, right? So now at every stage, once you have got an output, for the next stage that becomes the input. That's typically how it was even in the feed-forward neural network, right? Once you compute a hidden representation, that's the input to the next layer. Okay. So I have some input at one of these layers, either the input layer or any of the intermediate layers, and I apply a filter on that, and that filter gives me some 2D output. It gives me one feature map, and let's say this is what the feature map looks like. Okay. Now what does the pooling operation do? So I would apply 2 cross 2 pooling with a stride of 2. So let's see what that would do. That means I look at this 2 cross 2 region, I'll pick up the max value from there. That's why this is max pooling. Okay. So the max value is 8, I'll just keep that. Then I'm going to do a stride of 2, that means I'm not going to place it on this block, I'm just going to shift to the next block. Again, I'll take the max from there, which is 4, right? And I continue this, and I get this as the output. So you see why the shrinkage happens? Because I'm taking a 2 cross 2 area, and I'm shrinking it by picking up only one value from there, right? So it actually kind of halves the width and halves the breadth, so total of 1/4 reduction is what you get. But you could also use a filter with stride of 1. So this is what it would look like. So you will place it here, take the max value, then the max value, then the max value, and so on, right? So in that case, you will get a lesser reduction. And instead of max pooling, you could also do average pooling. That means instead of taking the max of these 4, you could take the average of these 4. Is that fine? So is the pooling operation clear and how it results in the reduction of the size of your input? Okay. So now what we'll do is, now that we have some idea of what a full convolutional neural network looks like, so it looks like alternating convolution and max pooling operations. We know what a convolution operation looks like. In particular, we know that a 3D filter applied to a 3D input results in a 2D output, because we are not applying the convolution along the depth, we are just applying the convolution along the width and the height, right? So that's what we know so far, and based on this knowledge, now we are going to see some success stories of convolutional neural networks, right? So we'll start with the first one, which is LayNet 5. So this was already the 5th version. This was around 97 or 98 or something, and I had mentioned this when we were doing the history lecture. So this is the input. Now you have decided to apply 6 filters. You have said that the stride is going to be 1, that means you are going to place at every location. The spatial extent is going to be 5 and the padding is going to be 0. Now the question that I have for you is, how many parameters does this convolution layer have? What are the parameters here? The filters, the weights in the filters. How many filters do you have? 6. How many weights does each filter have? 20? 25, right? 5 cross 5, so 25. So the total number of parameters is 150. Now I want you to appreciate something here. So the input was actually 32 cross 32, which I believe is 1024, and the output was 28 cross 28, right? That's what the output you got. That is, I guess, 784. Yeah. So in a feed-forward neural network, if you had x belonging to r raised to 1024 and your h belonging to r raised to 784, how many parameters would you need? 1024 cross 784. How many parameters do you have here? 150. Much smaller, right? This is because of both sparse connectivity as well as weight sharing, right? So now you appreciate the difference between the two, okay? And that's one of the reasons that even before, this is for example from 97, 98, 1997, 1998, right? So even before the deep learning wave of 2006 or the revival after 2006, right? Convolution neural networks were still being trained for even deep networks, 4 to 5 layers, because they had much fewer parameters, and that's why it was relatively easier to train them as compared to a very dense feed-forward neural network, okay? So I want you to appreciate that fact. Now after this, I have the pooling layer, where I'm going to use a stride of 1 and f equal to 2. That means I'm going to pick up, okay. So now I'm going to use the max pooling layer, where I'm decided to use a stride of 1, and the max pooling will happen in a region of 2 cross 2, okay. And again, k is 6 because there are just 6 filters. So max pooling happens on every feature map independently. It does not happen across the depth. That means I'm not going to pick the max along these 6 layers. I'm going to pick the max along each of these feature maps. So it's a per feature map operation, okay. And this, since it's a 2 cross 2 filter, it will result in a size reduction, and from 28 cross 28, I'll get to 14 cross 14. How many parameters does the max pooling layer have? Wow, good. There are no parameters in the max pooling layer because you're not having any weight matrices. You're just taking the input and applying a simple max operation on that. There is no W transpose X or any kind of a transformation happening there. Okay. Now this becomes your input. What's the size of this volume? 14 cross 14 cross 6. Okay. So all the filters that I'm going to use from now on, what is the depth of those filters going to be? What's the depth going to be? I want everyone to answer. 6, right? Because we are always going to assume that the depth of the filter is equal to the depth of the input. Now here they decided to use 16 filters. And by the way, you did hopefully notice that this 28, how did we get it? From which formula? W1 minus F plus 2P plus 1, right? So that's the formula. Okay. So now you have a 14 cross 14 input and you have 16 filters. So what's the depth of the output volume going to be? What's the depth of the output volume going to be? 16, right? And okay, so you have 16 and you have a spatial extent of 5 cross 5. Just a minute. Spatial extent of 5 cross 5. How many parameters does this layer have? I want everyone to say it. 400, okay. Fine. So that's, oh, there are 16 of these. Each is 5 cross 5. Oh, into 6, into D. Okay, okay. Good. Oh, then we made a mistake here also. Oh no, there the depth was 1. How do you get it? How you got 2400? Right? We forgot about the depth. So each of these filters is 5 cross depth. Right? What's the depth? 6, the same as the input. Right? So each of these filters is 25 into 6, which is 150 into 16. Yeah, okay. Fine. Is that okay? Did I confuse you or everyone back on track? Pooling layer, S should have been 2 because of that half reduction you're saying? Yeah, maybe. Can we just check this? Okay, I think it should be 2. Okay. Yeah, there was a question. Huh? Go from the pooling layer to the next layer, from here to the next layer. Okay. So now what's the depth of your input volume? 6. And what's the width and height? 14 cross 14. So now every filter that I'm going to apply at the next layer is going to have a depth of 6. So I've decided to apply 16 such filters. Okay. So what's the depth of this layer going to be? The depth of the output is equal to the number of filters. So the depth is going to be 16. And all my filters are 5 cross 5. Okay. But what we forgot is that when I say the filter is 5 cross 5, it is actually 5 cross 6 because the depth is also there. Right. So it's width into height into depth. So that's this number of parameters in each of my filters. Right. And that's 150. And I have 16 such filters. So that gives me a total of 2400 parameters. Is that fine? Okay. Okay. So now we have a volume of size 16 cross 10 cross 10. Now I'm going to do max pooling on that. Maybe again this should be 2. That's the same doubt you had. Okay, fine. So it will result in a reduction in the output. And now what's the volume, what's the size of this volume? 5 cross 16. Okay. And the parameters is 0. Max pooling layer does not have any parameters. Now after this what we have is something known as the fully connected layer. Okay. So now as I said, the size of this volume is 16 cross 5 cross 5. It's arranged in these feature maps, but I can always flatten it to get one single vector. Do you get that? So from these 16 feature maps, each of 5 cross 5 size, I can flatten it out and get a single vector of size 400. Do you get that? Okay. So that's what I do in the fully connected layer. So now I'm going to flatten this, treat it as a single vector, and then fully connect it to the next layer. What do I mean by fully connected? Dense connections, no more sparse connections. So now we have a feed forward network from this point of view. So you have 400 and that connects to a layer of size 120. So what are the number of parameters? 400 into 120 plus we'll have 120 biases. Okay, so that's what this number is. Fine. So this is one fully connected layer of size 120. After that I have another fully connected layer of size 84. So the number of parameters would be 120 into 84 plus 84. Okay. And after that I have the output layer. So the output layer, this was 26 or what's the output? Oh, but this is alphabet recognition, right? Okay. So probably they have done the computation using 10, but it should have been using 26 as the output layer, right? Because you want to predict one of the 26 alphabets. So you can assume this is 26. So it would be 84 cross 26 plus 26, right? That's the size of the output layer, right? Now, do you observe something immediately? Is there something very striking immediately in terms of the number of parameters? The fully connected layers clearly dominate, right? Here we are dealing of order 2400 at max, and here we just start with 48,000 itself, right? So just keep this in mind that the fully connected layers have the largest number of parameters that you have, and we'll try to come back to this and see if we can solve this problem. Okay. So now when you see a convolutional neural network, you should be able to reason about the following things. At each layer, what is the size of the input volume? What is the size of the output volume? What are the number of filters being used? And what are the number of parameters in that layer, right? If you can reason these things, then you have really understood what is actually happened. And unless you can reason these things, I don't see how you can efficiently code it up, right? So you should be able to know that this is the size of the input, this is the size of the output, and so on. And I guess all of us are comfortable with that. So now how do we train a convolutional neural network? What's the answer? You're nodding, that means you don't know, or you know, or it's too trivial to even ask this question. How will you train it? But how do you backpropagate through a convolution operation? That's a very nasty looking operation. Okay. a CNN can be implemented as a feed-forward neural network, with what being the difference? Only some of these weights would be active, all the gray weights will not exist, only the colored weights will exist, right? Now can you backpropagate to this network? Have you seen something similar before? Dropout, right? So if you could do that, you can do this also. So now if you take this view of a convolutional neural network, so this is just to give you an intuition or make you feel confident that once you know the backpropagation algorithm, there is nothing much different from training a convolutional neural network operation, okay? So everyone is fine with that. How many of you agree with that you can actually train using the same algorithm with some smart coding required to make sure that these weights are not active and so on? But in practice, of course, you will not do this. In practice, you will define the convolution operation. You'll also define the derivative of the convolution operation and then use that, right? Because that would be much more efficient. This is very inefficient, right? Because you are assuming that there is a fully connected network and then some things don't exist there. So that's the whole point, right? I mean, you wanted to avoid such dense connections, right? But in principle, you could have just used this and trained the convolutional neural network. In practice, you don't need to worry because you just need to define your forward convolution operations. And people like Google and all who release TensorFlow, Torch and all will do the hard work of doing the backpropagation for you, right? So you never have to write backpropagation in your life apart from what you have already written in the assignment, right? That's why I make you go through that torture once. So now afterwards, whenever you use any of these platforms, PyTorch or Torch or TensorFlow, the backpropagation comes for free. You just need to write the forward propagation. That means you just need to write convolution operations and you don't need to worry about how the derivatives will be computed. But what I want you to understand is that conceptually it's the same. You can still use, or in fact you still use the same backpropagation algorithm to train a convolutional neural network also. Everyone is fine with this? Okay? Okay. So now we know how to train a convolutional neural network also.